Hello, my name is Paula Moyano, and this is my project for Lab 1 on constant velocity. So I'll be going over the procedure, uploading everything to a tracker, gathering the data, and my conclusions. So this project put Newton's second law to the test by observing a real-life object in constant velocity, which is not common in the real life, but we're observing an object in the moment that it's in a relative constant velocity, analyze that data with a tracker, and then using the predicted data produced by a computational model to compare to the data collected by the tracker. So to do this project, I rolled an object across a flat surface, recorded the distance of the roll and the time it took to roll across that distance, then uploaded a video of that onto a tracker software, and gathered the data that the tracker gave me into a glow script using the code we were given, and then compared the computational model to the data analyzed by the tracker. My system for this project was a water bottle, and the surroundings were gravity, friction, and any applied force. This is the video uploaded to the tracker of the water bottle rolling across the surface. The red dots following this relative center of the water bottle are markings of the center of mass of the water bottle at each timestamp that I recorded by hand. On the right, you can see all the data being gathered, the time for each position. And at the top right, you can see a graph compiling that data of time and position. Then the data I gathered was that the distance was 0.4 meters. The mass of the water bottle was 0.212 kilograms. The time it took to roll across that distance was 1.8 seconds with 0.014 seconds per frame. Then to calculate the velocity, I used the velocity update formula, which says that the final velocity equals the initial velocity plus the net force divided by mass times the change in time. Now, since this is a constant velocity, Newton's second law tells us that net force will be zero, which makes the whole right side of the equation zero, which means that the final velocity equals the initial velocity. So the average velocity will equal the change in position over the change in time, which in this case of the water bottle is 0.222 meters per second. Here is the code I uploaded into GlowScript. I changed the mass of the water bottle, which in the end does nothing because mass gets canceled out, and the time and velocity. Here are the two graphs. The one on the left is the one that produced by the tracker, and the one on the right is the one produced by GlowScript, the computational one. There are clear discrepancies between the two, as can be seen here. So the green line is the computational one, and the red one is the one produced by the tracker. You can see that the computational slope is much larger than the tracker slope, and this could be for many reasons. Some reasons being errors by me, human error, so errors in tracking the center of mass might not have been correct, or errors when pushing the water bottle, any surroundings like friction or air resistance. The tracking of the center of mass, as I said, could have not been very accurate, and any rounding issues, inconsistencies when rounding numbers. So in the end, the computational model very closely resembled the tracker data but had some deviations. The tracker data did not show a perfect constant velocity. The line was a little bit jiggly, and the slope being much smaller than the computational model's slope. Could the axis be flipped? Yes, the axes could be flipped with no problem. The graph would still show pretty much the same information, but sloping in the negative direction. We cannot calculate the pushes and pulls because there are so many external variables that could be adding gravitational force onto the water bottle, so many surrounding objects that could be affecting it. In gravity, friction, it's really impossible to calculate. Thank you for listening.